In this video, I'm gonna show you a new method for solving range minimum query that you've never seen before, called Arpa string. I'm Ackermann, and here is Algorithmy Academy. Today, we want to have our first part of range minimum query. And this part, I'm gonna show you my trick, Arpa trick, a new method that solves RMQ. So let me tell you the problem description again. Actually, I expect you to see the parts before, but let's repeat. So problem has description in its title, given an array and queries of type LR. Each query asks for minimum in the range from L to R. So as you can see in this example, in the query range, the minimum element you can find is 2. So the answer is 2. First, let's start with talking about why this is so-called Arpa string. Everything goes back to round 383 of Codeforces, where the last problem of first division was a problem that needed RMQ. And so for that problem, I invented something new, some new algorithm for solving RMQ. And yeah, I was super happy that I invented some algorithm. After the contest, I published a blog on Codeforces named Arpa's Technique, and I published my results and performance tests and code and everything. And actually, people came and said, we were currently using this in China, or some other coders say something like that. So that was the reason that I understood that before me, seems that Tarjan did discover this algorithm. So I removed that blog, but people started to ask me to revert it back, and I published a new blog on Codeforces named Some Method for Solving Range Minimum Query. And then after a few years, people started to call it Arpa string. So I got a message from a friend asking, so what is this? What is Arpa string? And he sent me a link from CP algorithm, and here they were mentioned that this algorithm is Arpa string. And now if you search in Google, you will see people are explaining Arpa string and so on. But the fact is, all of these things are not that true. They are partially wrong. We'll discuss it in this video, and we'll show you the real Arpa string. As always, I ask you to think before I want to tell you the solution. So to give you some hint, try to map the problem to a graph. Try using some graphs to solve this problem. Think for at least 10 minutes and then continue. Let me tell you a hint. The graph you want to build is connecting every element to the first next element is smaller than it. Like 5 is connected to 3, and then 3 is connected to 1. Or for example, 2 is connected to 0, but 0 is not connected to any other element. Try to think about this idea and invent an algorithm that solves RMQ. And again, pause and think for at least 10 minutes and resume the video. So as I said, we are gonna build somehow a rooted forest, or rooted trees. There are some rooted trees, and there are some edges directed to the root. You can see here. So we connect every element to the first next element is smaller than it, like as you can see, and for sure there is no loop, right? So let's start with answering queries that end at the end of the array. So always remember, in our videos we follow zero-based indexing, and closed open segments. So when I say R equals to N, it means that we are including all of the elements that are a suffix of the array. So for example here, let's say query is asking for minimum of the range 4 to 12. 12 is the size of the array. So for finding the minimum of this range, what we need to do is just finding the root of element 6 at index 4, which is at index 8 and this value 0. So we go from 6 to 2 and from 2 to 0 and we found the answer. So, but now let's see what happens if we want to answer for some random R. We need to only consider edge ending before R. So like here, if I consider other edge like edge exceeding R, when I calculate the root for 6, it will become 0, right? But I don't consider that. So I only include edges that they end before R. Like as you can see, we have 3 edges like that. So for this query, I want to calculate the minimum and it goes from 6 to 2. So is that clear? This is very simple, right? You want the minimum of your range. It's either the first element or it's the next element is smaller than L, or it's the next of next, or it's the next of next of next, and so on. Unless it goes over R, that is not acceptable. So we need to follow these edges until we pass R. So we should not pass R because we want minimum of this range, right? So we can answer queries like this very easily. So here minimum is 2, or like this, answer is 1. Why? Because first we go from 0 to 1, index 0, index 1, and then we go to index 2. Every time we are going to a better answer, and from 1 we'll go lower. We'll not go to 0 because it's after the R, right? So here is the Arpa streak. Arpa streak says sweep from left to right. Sweep from left to right. Process elements one by one. And we answer queries offline. So we answer every query when we arrive at its end. So for example, consider the query 10, 15, that it wants minimum from 10 to 15. We will process this query when we arrive at 15. So it's a sweep line, right? We are sweeping the array. So when we arrive at index I, we do two things. Note that at the beginning we don't have any edges, right? So we only include edges that are ending before I. And when I is 0, we don't have any edges. So we go from I0, 1, 2, 3 to n minus 1. And what we do is when we arrive at index I, we already added all of the edges that end before R. So we are ready to answer queries that they end at R. So we just need to find the root of L for each of these queries, as you saw in the previous slides. So we calculate the root and we print it. And finally, we should add new edges that they are ending at R itself. So there might be some edges that they are ending at R and we didn't add them because we only added edges that they were strictly before R. So we add them and we go to I plus 1 and so on. So two things remain. One is how to find the root. Simply we use DSU, that's it. And the other one is how we find the first next element is smaller than, for example, element I, that we'll use monotonic stack for that. So Here is a sample code. So for each I from 0 to n, first we answer queries, and then we have some stack, monotonic stack, and we start popping elements smaller than this, and we set the parent of those elements to I. So it's a new directed edge. So here is a sample code of Arpa string. For each I from 0 to n, we do this. First we go answer queries, as we mentioned. Then we have some monotonic stack, right? We start copying the elements bigger than I, and we connect them to I. So we set root of this element to I, one by one, we get them and we pop them from a stack, and finally we push them to a stack. But I want to tell you that you don't need to use monotonic stack for that. So stay tuned, we will publish a video on how we can calculate first next element is smaller than I without using any stack at all, very simple. But all these things, all orchestrated on CP algorithm, on my blog, everywhere, they were wrong. So this is wrong. This is also wrong. Why they are wrong? So there are 3 versions of DSU actually, at least. So first is what using some size conversion. So you calculate which one is bigger and you connect a smaller to the bigger, right? This results in O log per query and it's deterministic. Second one is using path compression, which works in O log in amortized. Proof for this is not simple, but you can search, and there is an article from Tarjan explaining this. And finally, the mass proportional DSU is using some size conversion plus path compression, which this results in Ackermann inverse of n, which is very, very small, right? But the implementation published everywhere for Arpa string uses the second version of DSU. So they are not actually all Ackermann inverse. They are all log. So all of them are not wrong. But yeah, let's fix the Arpa string, which is actually not that hard. So first, let me explain more why we can't use the normal DSU here that we used before in normal problems. So in normal problems, you have some vertex A and B, and you want to join these two together, right? So first, we find root of A and root of B. Let's name the RA, RB. Then we compare sizes, and we connect one of them to the other one. But here we can't do. Why? Because you remember, we connect the bigger element to this new element. Like it's a directed edge. But in DSU normal problems, the edge is not directed at all. But here we have directed edge. So if you connect this to this, that actually happens in most of the cases because element of the size component of this element is for sure bigger than this, or at least equal, because size of this is 1 and size of this can be more. So if you compare sizes and connect smaller to larger, it happens that you connect I with the first bigger element to the left and it will not work. So we will fix this like this. For each DSU component, we keep the rightmost element of this component too. So when we are merging two components in our DSU, first we connect the smaller to greater. So it's now size compression, and we were using path compression to So it results in O Ackermann Inverse in amortized, right? And also when we are merging, for this new component that we are making, we make sure that we are keeping the last index of it too. So we set last index of it to the maximum of last index of it and last index of the component that is merging with it. So always we have the last index and we can solve the problem. But here I have a note that from what I heard before, almost always only using hash compression will be in practice faster than size compression plus hash compression. So now let's start the implementation to see how Arpa tree can be implemented. So we'll start with getting the array. And then queries, and we need a vector here, which means that which queries are ending where. And we are implementing the code closed, open, and zero based. So this is what you are seeing here. And now I start the main loop that we are going to calculate the answer. And here I'm gonna use the stack, but yeah, I told you that we don't need to use the stack here, but we'll provide another video talking about this. So if the last element of a stack is larger than the current element, let me define the DSU struct here. And like this. And I fill all of the pair elements -1, and then I fill the last array like this. So fills an array, and iota is like setting the first element to 0, and then 1, 2, 3, 4, and so on. So if this is the case, I merge, and let me find DSU here. I will merge st.top and I in the DSU. How I will do it? First, I implement the root function. Then if they are from the same component, actually it never happens in our problem. So because every time we are trying to merge I to j, we already know that I is root of another component, so they are for sure never in the same component. And then if this is the case, I swap I and j, and you know, in this version of DSU, either pair is positive, that means it's pointing to another index, or it's negative, that it says that I is root itself. And if pair I is smaller than pair j, it means that actually j is a larger component after swap. So here we know that pair j is smaller than pair I, so j is root of larger component. So we set pair of I to j, but before that we set pair j plus equal pair I. And also here we need to make sure that we set last of j to be maximum of last j and last I. So we are merging these two elements, and yeah, that's it. This part seems good to me. And we pop this element, and finally we push I, and here we answer queries, and answer to this query is DSU of root of component of LQI, like this, and then last of it, because the root itself, it's not the answer. In the old Arpa string it was, but now it is not. So in our new method that we optimize time complexity, last shows the last element of this component, not I itself, not the root of this component itself. And finally I print the answer. That's it. Let me come with a sample like 5, 4, 1, 2, 3, 5, and single query from 1 to 2. Okay, this is correct. From 3 to 5, it is not correct. So yeah, we need to do this because it's just pointing to the last element, but we need to take the element itself. But yeah, it's not working again. So let me print some information that how edges are. So this is true, there is only one edge in our example, and oh, got it. We need to continue to here because this query ends at the nth element, and here we need this if. So now this is correct, and let me run it again. This is correct too. So let me submit this code to see if it's gonna work. Finally, I think that in this problem it was better to maybe use closed like here using minus minus R to not adding this if and yeah, neater implementation, I think. So we did something not that optimal. Okay, we got wrong answer. Let's see what happened that it resulted. Oh, it's already zero-based indexing. So what I need to do is changing my indexing. And yeah, we need to change the order of processing queries, because first we need to process, yeah, now it's true. Let's submit again. And we got accepted. Thanks for watching. If you found this video useful, please like, subscribe, and ring that bell. By the way, YouTube thinks the video down here is just perfect for you. Give it a watch and let me know in the comments.